Let's switch over to, wait, it was muted. I didn't unmute. Okay. Exactly. All right, cool. Well, see, it all worked out. All right. We are now in a brilliant new week of Computing 101. So let's take a quick look back where we just came from. Starting with how cryptography went, I think the TLDR is it could have gone a little better. Definitely as we refreshed the modules, maybe we overshot here. The median grade was a 54. But the nice thing is the majority of the students hit the checkpoint, the vast majority. So 93% of you hit the checkpoint. Likely then the median actual grade out of the 10% that this module is of your grade is closer to 7.5 or something, which I guess is actually not that bad thinking about it that way. But definitely on the harder side of what is expected. We have some good ideas. We'll release the survey soon. Hopefully that'll give us more ideas to improve that approachability in the future. But you can see this this kind of bell curve over here. It's a module. All right, who loved cryptography? All right, who hated cryptography? All right.
Most of the hands for those at home.
Yeah, most of the hands hated cryptography, but that's okay. Cryptography truly is the type 2 fun, right? Most of this class is type 2 fun. Type 1 fun is the fun that you know you're having while you're having it. Type 2 fun is when you don't know that you're having fun until you look back on it later. While it's happening, might not be so fun. So crypto, definitely type 2 fun. The camera is not following me. Let's try to get it to follow me. Awesome. There we go. Okay. All right. So that's crypto. Definitely overshot on the difficulty level, or maybe the approachability level. Maybe we've been talking about, okay, maybe we remove base 64 from this. Maybe we make re-implement this not in Python. Anyways, there's a lot of different options. TLDR though, for this semester, we're going to change the late penalty of crypto from you get 50% credit to 75% credit. That's through the day that grades are due, which is the 16th of December. So if you have some spare time and you want to revisit some crypto, please revisit the crypto. It'll still be worth it in a lot of ways. So if you hit the checkpoint and then did the rest of crypto late with this, you'd still get a pretty reasonable amount of points on that. All right, that's crypto. How did access control go, which was due on Sunday? Access control went very, very, very differently. The median score in access control of 94.74. So that's everything but level 19. That was the median performance on it. Oh, pretty good. Yeah, great job on access control. Very different curve here. Of course, access control is way, way, way too easy. We have ideas to rectify that as well for next semester, and to get everyone learning a little bit more things. All right. Questions on that? Sweet. I don't think my chat has actually loaded on Twitch, unless no one's chatting, which is possible. Oh, there we go. Okay, cool. So let's roll onwards. Okay, with that out of the way, how are people doing in general? The current grade distribution by percent in the class. You can see is that blue on the right? that is passing. Yeah, the blue. There's people that are passing the course. That is a C minus or above. I guess there's no C minus. A C or above. And then on the left of that, the yellow, green-ish, is people that are not passing the course. And you see we have the left side of a bell curve, right? And the height of that bell curve is probably around 95. So this tells me that maybe the class is a little too easy. What do you think? Maybe make things a little more challenging so that the height of that bell curve is right around a solid B. All right, people are saying no. All right, anyways, but it is somewhere in a reasonable spot. There's definitely a hard class, but people are doing fairly well. If you look at it from just the letter grades, A on the left there, E on the right, we have a failing rate of about probably 16, 17%. That's D and E altogether, which is somewhat within an expected range for a third-year course. And then we have a good distribution of people getting A's, B's, and C's. So pretty.
And all of this is still without extra credit.
Yeah, and this is still without extra credit applied, which we are working on automating the application of soon. Yeah. Oh, the chat doesn't refresh completely. That's weird. Okay. Awesome. All right. And then we, of course, have the helpfulness battle that Hanzo continues to dominate. Rob and then me and Connor pointing the way forward there. And then shout outs to Iron, Biting the Bits, and Chaptoan, username 1337, specifying Cool Wolfie 96. Many of those names are new on the leaderboard here. Good extra credit and good helpfulness. Thank you. And with that, we're moving on to Computing 101. Computing 101 has basically absorbed all of our introductory material to assembly, to how your computer more or less truly works on the inside, how the programs are actually running, etc. This is stuff that ideally you learn before hitting this class in computer organization, but there are a couple of problems with that hope, and they kind of conspire together to make it so that we have to give you a crash course into computer organization in this class before hitting the rest of the material. So the rest of the year is going to be pushing through computer organization, basic assembly, and so on. And then going into reverse engineering of software, going into exploiting memory errors, and then putting everything all together, everything so far in the class, to really pull off some awesome hacks. Cool. Any questions? All right. So let me show you. Did we add it to the class itself yet? All right. We'll add this to the class itself shortly. So it'll show up over here. But for now, you can grab it over here in Computing 101 at the top of the page. This is, if you click on Dojos, Computing 101. And Computing 101 has 6 modules. The first 3 get you through writing your very first assembly program. And we're going to actually tackle one of these just to show you how to interact with these challenges. Assembly crash course goes into a bunch of different scenarios, different assembly instructions that you'll practice, different types of logic you might implement with assembly. Debugging refresher will show you how to debug your assembly code when it goes wrong. And building a web server is a awesome end-to-end project where you will actually build a web server in pure assembly that'll allow you to serve up pages that you are kind of well familiar with the Python equivalents of. This is all Computing 101. Over the next 2 weeks, we'll tackle all of these. The checkpoint is on Sunday, and then we'll go on from there. The checkpoint for these 65 challenges is at 20, how many? 21? Something like 21. That'll get you through into assembly crash course. My advice is to push as far in as possible on the checkpoint because these are, especially later on, not easy concepts. Like we give you 2 weeks to work on this, and most people, they rush through the checkpoint, they ignore it until the final weekend. That's going to work about as badly here as it did in crypto. So please don't push it back. Okay. Questions on this assignment before we move into actually messing with assembly? All right. Okay. Let's get into some assembly stuff. Why is Twitch not working well? One sec. Let me restart my Twitch chat here. All right. I think this should be good. Now I can at least see it reasonably. Okay. Awesome. So, let's dive in. We'll grab our first program. First of all, please, I'm going to not cover the concepts in these lectures. Please go through and catch up on all of the lectures, starting from your first program and going through all of them. There's, some of these lectures are attached to more than one module. Watch all the lectures in all the modules. It'll really, really, really help you. There are probably about 12 mini lectures in total, each of which is, how long is this one? Yeah, 13 minutes, 10 to 13 minutes long. So please watch all the lectures. Okay. Let's dive in. So we're going to dive into setting our first register. There's a lot of good documentation and information for you to go through. Don't ignore that either. What's our special demo guy?
Nice.
Awesome. All right.
Oh, I stole the camera now.
That's good. Okay. So let's learn about assembly. We're all familiar with cat/flag, right? Let's make the flag readable. I'm in practice mode. Cat/flag reads the flag, right? Cat is a program that might be your favorite program. Who here's favorite program is cat? One person. All right. Two. Okay, we got some cat fans. Because, eventually you do cat flag and you get the flag. But what actually happens with cat flag? What is cat? Well, one way to implement cat, because you've all been writing Python scripts, is let's implement it in Python. It's we import sys to get the arguments, and we'll just implement a very simple one. And we'll print open sys.argv1 dot read, and we got a cat. And we should actually make it runnable. Okay, we can run cat.py/flag and we're good to go here as well. Awesome. Okay, so that's one way to implement cat. But what does all this actually do at the end of the day, right? At the end of the day, cat talks to our operating system. It asks the operating system, hey, please open this file. Please write this file to the terminal, write this, or please give me the content of the file. Please write this data to the terminal. And we can actually see interactions between the operating system and the program if we use something called strace, right? And strace here, you can see all the interactions that cat has with the operating system. And it's a bunch of stuff, but if we scroll all the way down, we can see something really nice. Here's open. It says, hey, please open /flag in read-only mode. And then it opens it. And then it says, hey, let's read from the flag. And then this is what it actually ended up reading, right? And then it says, hey, please write these contents. And here is that data appearing. Very cool. So cat talks to the operating system using something called system calls. You learn a lot about these in this module. But what does it actually do? What's the internal logic? Now we've talked about the external interface between cat and the world. It's these system calls that it uses to talk to the Linux operating system with. But what about inside cat? Well, inside cat, just like inside you all, is a big hodgepodge of organs and stuff. Inside cat, it's a bunch of computer instructions. It's all computer code. And we can look at it. We can do this. Whoops. And actually, well, yes. Let's do this. We'll disassemble cat into its constituent instructions and print them out. And now we can actually start seeing what is cat. This cat as a program, even though it's very simple, it just prints files to standard out, it's actually pretty complex. There's a lot of instructions here, right? So let's write our own cat, not in Python, but in C. It's a little, should we write our own cat in C?
Let's do it.
Let's do it. You're right. What are we afraid of? Okay. Here we go. Writing it in C. Who here has written C before? Perfect. All right, almost everybody. I don't have to teach you guys C. Okay, so we're gonna use, who here has used F open, F closed? We're not gonna use that stuff. That's higher level things. We're gonna talk straight to the operating system, the beautiful, beautiful language of system calls. Say, okay, we're gonna get a file descriptor by opening /flag in read-only mode. Look familiar? It's more or less what we saw with the strace. We're going to have a buffer, and no one needs to read more than 1024 bytes. So now we're going to read from this file descriptor into this buffer 1024 bytes. And this is how much we've read. And then we're going to write to standard output. Who here remembers from the Linux Luminarium? Standard output is file descriptor 1? Nobody. All right. Couple of people. Okay. Awesome. We'll put that on a test one day. Okay. From the buffer of however much we read. And now we are basically good to go. We'll exit for good measure cleanly. Oh, yeah, it's return 0. Okay, perfect. We got everything. Probably unistd.h. It'll tell us if we don't have something. So we're gonna make this program my cat. Actually, it's a little mini version of cat. We'll call it kitten. Okay. Wow, beautiful. Okay, kitten /flag. Boom. Amazing. All right, now we have our own little mini version of cat that we've compiled. That's much simpler than Big Cat. Big Cat has all this crazy stuff like -- help, right? And that prints out its help. All of this is code that's in that binary that we were just scrolling through. So now if we disassemble kitten, here is kitten. That's it. It's much, much smaller. It's got a bunch of administrative stuff. But the key thing of kitten is here. Here's our function main. And here are the assembly instructions that implement all of the operations that kitten does. Those 4 lines of C that we wrote, these are all of them. Ret, you can kind of imagine, especially because of the last instruction, it returns from the function. That's our return 0. We kind of glance at this, just like not knowing anything about it, just trying to pattern match a little bit. That 0 is probably what we're returning, and it is. If we look, there's something read here, right? And you remember in our C code, we read from the file descriptor. Here's an open. Awesome. There's a write. Here's the write. There's a 1, our standard input, right? And we see these 0s and 1s, they are arguments here, arguments to the move instruction, right? And so we're moving a 1 into some storage, which is a register, and etc., right? None of this makes sense yet. But watch the lectures, start tackling these challenges, and this is what you learn step by step, instruction by instruction, until you are building your own web server, right? Okay, so let's take a look at this level. I'll show you how to write the assembly that this level needs. And then over time, over several different modules, we'll go through different ways of creating, writing assembly, creating assembled binary files like cat and kitten, and passing it into these programs. All right. So first things first, we're going to talk about registers, right? Here, they're all these different 3-letter words. There's RSI, RCX, EAX, RBP, RSP, and this sounds very, very confusing, right? These are all different registers inside your CPU. What's a register? Who here has short-term memory? Probably everybody. You have long-term memory, you have short-term memory, and you have working memory, right, as a human being. Your working memory holds about 7 items, right? If I rattle off 7 words at you and then have you recite them back to me, statistically speaking, you'll do fairly well. If I rattle off 12 words at you and have you recite them back, you're going to drop a lot of those words. Forget them. If I do 30, it'll be harder and harder and harder. You'll have to start writing things down. You'll have to start coming up with mnemonics to put in your short-term memory, and so on. Registers for a computer are working memory. A computer, your CPU, running inside your laptop, your phone, your microwave, that CPU, when it executes logic, it tracks small amounts of data to make decisions, to reason about its work, et cetera, et cetera. It tracks that data in registers. And these registers are physical things inside the CPU. This RCX actually has a physical set of transistors that makes up RCX in the CPU, right? And those transistors, because they are so centrally located in the CPU, their CPUs nowadays are fast enough that like light speed effects come into play, that heat dissipation is a big problem. You have very few, a very limited budget for stuff that you can stuff into a CPU. So there's very, very few of these working memory type registers, right? Very few of these. On modern systems, depending on the processor, you might have on the order of 30, 40, right? If you really, really scrape the barrel. On x86, you have about 15, 16 easily usable general purpose registers are these. And these hold data, right? And you store data into these registers using an instruction to the CPU called move. You say, hey, I want to move hex 420. No, that's not a move. I want to move 0 into EAX. Everything that cat tries to do internally within the CPU is an instruction. It moves 0 into EAX using an instruction. Here, it's preparing to make this write to the terminal. It moves 1 for the standard out file descriptor number in Linux into EDI as an instruction. And this instruction that we've disassembled cat into, or this instruction that's one of the many instructions we disassembled cat into, is stored in the cat file or the kitten file in this case as a bunch of bytes. It's BF01000000 is move EDI 1. It's a mapping, almost direct mapping from the assembly to the bytes. And we have taken kitten, and let me actually show you come on, I want another. Yeah, there we go. Another window. Okay, there we go. It's just loading. Okay, we have taken here we are disassembling this kitten file. We can also hex dump it. You're now very hopefully well familiar with hex and looking at things as binary versus hex versus etc. And we can hex dump kitten. And here's the kitten file. And somewhere, if we pipe this through less and we search for B1, was it B1? Oh, BF01. Okay. If we search for BF01, search for BF, there it is. Here's our move. Here's that instruction. BF01000000 is right here. Our move EDI 0. Maybe there are multiple occurrences of that instruction. Here's one, and then the next one is E885FE, blah, blah, blah. So let's look here. E885FE, blah, blah, blah. That part of the program file translates directly back into this assembly, which is generated by the compiler when it compiles C code on its way to becoming binary, right? So if you look at kitten, let's move cat.c into kitten.c. There we go. So if you look at kitten.c, we have our program, right? We compiled it into the binary here. Okay, awesome. We obj dumped that back into assembly, but you know the compilation itself goes through an assembly phase, and you can actually just tell GC stop at assembly and output the assembly for the dash capital S. And output the assembly for cat instead of the binary, right? And this is the assembly for cat/flag. Now, you might say, hey, we were just looking at obj dump at the assembly that we got from the binary. It's reading the file, blah, blah, blah. Come on. Okay. And this is badass. This is super readable. Here's move. It moves data flows that way. It moves RCX into RSI. And you'll read all about this and view the lectures and do this a million times in the homework. But when we actually look at the produced assembly file, this looks like crap. There's a bunch of weird things, moval, there's percents. What does this mean? These are two different assembly dialects. Unfortunately, as we'll discuss in the materials, historically, when x86, the modern great operating system running many of your laptops, unless you are living in the future, x86 was created by Intel in their brilliant wisdom, and Intel created the Intel assembly syntax, which is what we see here, which I selected specifically using this flag, right? And then some shenanigans were pulled at AT&T, which was one of the early researchers into operating systems, and the people that created at AT&T Bell Labs created C and so on, and they created their own assembly syntax called AT&T syntax, and that's what GCC produces, unfortunately. In this class, the official class position is that this syntax is no good. AT&T syntax bad, Intel syntax good. All right? Who here loves Intel syntax? Awesome. Who here loves AT&T syntax? No, bad. We like Intel, not AT&T. All right? Intel? All right, good. This is the college brainwashing you'll get in this class. Intel syntax. Okay, awesome. So both syntaxes represent the same file. If I was a worse mentor to you, I would delete this, hit enter, and you would be exposed to this AT&T syntax. And that's not very fun. Doesn't look very good. It just makes you sad. All right, whereas this makes everyone happy. Cool? Might seem small, but this is a very important philosophical position that we should all take. All right, awesome. So we now have instructions making up logic of the program And then this program eventually interacts with the Linux operating system to actually make things happen, such as characters appear on your screen, right? And what happens to cat.py is, of course, cat.py is executed using Python. And actually, this also ends up executing assembly instructions because we can disassemble user bin Python. Where's Python? And that is Python disassembled. You can see it's quite large. We can be here for a while. In fact, if you wanted to get a rough count of the lines of assembly in user bin Python, it is about 682,000. That's actually less than I expected. But that the Python interpreter, which interprets Python files and executes Python logic, is written in C and compiled into binary code, to which assembly is basically a one-to-one mapping. Right? So your CPU reads this binary code, these bytes. This is 1 hexadecimal byte at a time, and this instruction is 4 hexadecimal bytes. And you can actually see this 8, that's right here, just a direct mapping. This 1 that is added to RBX, here's the 1. Right? It's pretty cool view into what your CPU is actually doing. And at the end of the day, whether you're running Python, JavaScript, what have you, at the end of the day, your CPU is frantically executing instruction after instruction after instruction after instruction by reading bytes from memory, interpreting them as assembly, and carrying out what it needs to do. Any questions on this concept? Awesome. Okay, so now how do you write this stuff, right? So we created or kitten.c. We can also create, of course, kitten.s. We already have a kitten.s we generated from the C file, and it's not a bad way to start. Here's our kitten.s. A lot of this is unnecessary, and actually, we're just going to throw it all away because it's all AT&T syntax. We don't like that. So we're going to steal small parts of it. Well, we'll just show you how to write it. So blow this away. Should we? Yeah, we should. We should. Right? Yeah. Let's write it. Okay. Kitten.s. We write it very, very easily. We go, okay. We want to move some stuff, set up some registers. We are going to do something you will learn maybe 5 challenges in, which is how to actually talk to the operating system. This might be jumping a little ahead. Let's do this on Wednesday. Okay, we're going to do that on Wednesday. What I'll first show you is just how to interact with the actual challenges, right? So in this level, we write our first assembly, and we must move the value 60 into the register RAX. All right, we do this using the move instruction. So when we run the challenge, it says, okay, please input our assembly. We can move into RAX some value, hit Control D when we're done, and it says, oh, I moved the wrong value. All right, So that's how I interact with the first 8 or so challenges of Computing 101. These first, again, this whole thing is what's assigned, all of Computing 101. These 3 I can interact with just by typing assembly into, and they're very nice, and they will do the right thing with my assembly to make it into a runnable program. Because again, your CPU interprets binary code, whereas this interprets these levels interpret the assembly directory. But let's say I wanted to turn my assembly into runnable code directly, which I do for later levels. I can do move rx.s, and I can write this to a file. Okay. Now, there are multiple ways to create a binary file out of assembly. I cover one such way in the lecture where you will need in the module, in the part of this module, part of Computing 101, where you need to do that, which is assembly crash course. I'll show a slightly different way here, just for completeness sake. There's a a program called AS, the assembler. And AS can, let's see if we can do something. Can we have AS interpret Intel syntax directly? Yes, right? -m. Let's see, -m Intel 64. Does this work? And let's read in on standard input or move rax.s. Okay, see, it didn't work. Does it support -m Intel? Nope. Okay, can't open Intel for reading. There is a syntax, right? Man AS syntax. GNU syntax. Okay, hold on. Sudo. Yes, M mnemonic equals Intel. Is that enough? Let's see. We got to get this file system. Oh, yeah. It still didn't do it. Oh, -m syntax equals Intel. Thank you. I knew it was there. What's going on? Okay. All right, we're moving to temp because the file system access should be faster in temp. What's going on here? Okay. -m syntax equals Intel. Oops, not GC. AS. Move rax.s. Nope. All right. Here's what we're going to do. Of course, what's happening right now is that our standard tooling all expects AT&T syntax. It's not easy to be correct and use assembly syntax sometimes, but we don't do it because it's easy. We do it because it's right. So we can do dot Intel syntax, no prefix, right? We give a directive to the assembler that, hey, what's about to follow is Intel syntax. And then we just assemble things and it all works. And now we have an a.out that we just created. That is, if we disassemble it, contains if we disassemble it in Intel syntax, contains our awesome assembled instruction. And this is move RAX 123, which is 7B in hexadecimal. Cool? And now we can pass this to our program. And it doesn't work. Okay, let's try this. Some bug here. Maybe these first three probably only take assembly. Oh, okay, yeah, because I'm on the wrong level. Okay, so these first three submodules of Computing 101, you'll just be writing assembly directly into, right? Challenge check, move RAX 123, Control D, boom. Awesome. And then tells you you messed up. Of course, if you want to do it the right way, it says, it told me to move 60 into RAX here in the challenge description. If I implement that, hit Control D, bam, tells me I'm a good boy, shows me that the program crashed, and then tells me to keep going because the program was supposed to crash. It's the first level, it's your first assembly instruction, and it's all good. Yes. Can I what? This step I'll redo this a couple levels later right now where we actually need it. For this, these first couple of challenges where we're interacting, giving it assembly that it assembles itself, we don't need it yet. And then we get to the assembly crash course. And I'm going to run a challenge here and show you. The same challenge here, setting RAX to a value. We're going to do it in a slightly different way. And I will push an updated description later today so that it's not confusing. So here we are. You will need to do this as well for the checkpoint. This series of challenges is implemented slightly differently. When we run the challenge, it gives you a lot of instructions, and it actually gives you the instructions on exactly what we were doing there. How to write your assembly and how to assemble the assembly and how to extract the assembly into a dedicated file to pass into into this program. So let's do this again here. We want to set the register RDI to the value hex 1337. So we're going to create a solution script. In /temp. We need to fix this. Okay. /temp. We create our solution script. This is our assembly. Do our Intel prefix, no syntax, Intel syntax, no prefix. Okay, this is a directive that tells the assembler, again, that we're going to be using a specific subdialect of Intel assembly. And we want to set our DI to hex 1337. So now we're going to move our DI hex 1237. Okay, and then we'll follow the instructions here. We'll use AS, and we will extract the bytes of the actual assembly and pass it into the challenge. So let's do AS. So if we do AS solve.s, this assembles our assembly into binary. Okay, here it created this a.out. We're going to actually pass. What is going on? We're going to pass a solve.o. Okay, now it extracted it into or assembled it into solve.o. And then we're going to use this crazy command to extract just our assembled code out of this file. First, let's take a look at it. So we just can disassemble the assembled assembly that we assembled. Pretty cool. But if you look at the actual hex value of this file is actually surprisingly big, right? There's only 1, 2, 3, 4, 5, 6, 7 bytes of binary code in this file. But the file itself is huge. If you hex dump it, there's a lot of metadata in binary file formats. And this metadata we can read with objdump, which is the program we've been using to disassemble so far, but it's so much more. It is a general analyzer of these files. For example, in our solve.o file that we compiled, that we assembled from our assembly, there is a .text segment, which for historical reasons is the name of the segment that has looked up why it's called a .text segment and I forgot. Yeah. There's a cool reason for it. But this is the segment of the file that contains the actual assembled binary data, and then that size is 7. And that is what's actually disassembled right here, that text, when we run objdump in disassembly mode. Pretty cool stuff. Anyways, there's a bunch of, all this metadata takes up space. And because of that, these files are kind of bigger than expected, but we can extract just the .text segment using something called objcopy. And objcopy has a funky syntax that we can copy here. So we say, okay, we want to output a binary file from the section text of solve.o, and we want to output into solve.bin. This is just our assembled assembly, the binary that resulted from taking the assembly and converting it into a binary representation using the AS command. And then we can hex dump this, and we see our 7 bytes. Awesome. Then we can take this 7 bytes and cat them, pipe them into challenge run, and it'll execute our code. This is the code we sent it, and here's our flag. Cool? Yes. Okay. So when you're working with assembly, there are a couple of different concepts and different data representations that you have to keep track of. One is the assembly code you're writing. These first 3 modules are just that. You write your assembly code and you just paste in that code. So you don't have to think about how to convert that to binary, etc. The challenge does that. Awesome. Then there is actually making a program out of that assembly code and running that program, right? The first step of that is you take your assembly and you convert the assembly, the text, the move space rex, whatever, into binary data that your CPU interprets. That is closer to what we explore here. We truly explore it in building a web server. In building a web server, you create binary executables like bin.cat over the 11 levels of building a web server of that challenge series. You create more and more and more complex programs that in the end implement the web server that can accept requests. In the assembly crash course, we're just extracting, we don't have the full program, we're just extracting snippets of assembly code from these binary files and testing their core functionality. Not the whole program, but really just the instructions. And assembly crash course, this challenge series is a stepping stone from you just write your assembly to you're running your programs on your own. Here we are still executing the code, but you can assemble it and extract it for us. Cool. Okay. Now, assembly crash course exposes you to a bunch of different assembly topics. And then the next step is for you to learn how to debug your assembly when it inevitably goes wrong, right? Assembly crash course gives you a slightly easier way to do this. You'll learn the true complex way in this challenge run. But in assembly crash course, if something goes wrong and you want to debug, just get a quick snapshot of what was going on in the code, you can use a special instruction called int3. Historical reasons for why it's called int3, but this instruction will interrupt our emulator in the assembly crash course, our evaluation program, and it will give you the state of registers and memory at that point in time. And so if instead of 1337, we put in 1338 by accident, and it didn't work, let's see what happens here. I don't know why the emojis popped up. /temp doesn't help. Why?
Must be silly something.
Yeah. Okay, and then we do AS, and then we do obj, copy, and then we do this cat, and it says, whoops, it didn't work. And here it tells us why, but we're not always so lucky. So we're going to look at what we can do to add some debugging to just the assembly crash course series of modules. We can use this int3 instruction. Wait for it to save. Assemble that. Extract that. Run it. And every time that we hit an int3 instruction, the assembly crash course will give us a full dump of all of our register values. And here's our 1338 that we wrote to the register RDI. Give us the data on our stack, and we'll talk about this in the lectures of the module, and you'll explore it in the assembly crash course. And then contents of computer memory. And you will tackle all of this in the assembly crash course, but I just want you to be cognizant of this int3 functionality for debugging. So when you tackle this later, you get to this point, you're like, I really wish I knew what the value of this register was. Here, remember, int3. Okay. Debugging refresher. Once you make it through the assembly crash course, we'll teach you how to debug programs, how to use a debugger called GDB, the GNU debugger. That will become one of your best friends for the rest of the module, or for the rest of the class. And building a web server will put all of your assembly knowledge all together to truly understand how you go from assembly all the way to programs that run in your computer. Again, ideally, much of this conceptually is review from computer organization. But for various reasons, we still need to make sure to go through this, make sure you have this solidified in your mind. And we have 2 weeks for it. 65 challenges. Each individual challenge is pretty simple. If you solved challenge 1, you saw how easy that was. But don't put them off too far. Okay. Any questions? Yes. All right. The question was, if, as we saw, if you wrote kitten.c and it created kitten, the binary, and we didn't even have to think about assembly, why are we bothering to learn assembly? The answer is that going backwards from there is harder, right? So you can go from C to assembly to binary very easily. But in a cybersecurity context, if I give you kitten, the binary program, and of course, you can disassemble it. Wow. Gotcha. All right. Well, you can disassemble it as we've been disassembling. And that is a very well-supported thing to do. The tooling is very mature here. You can also try to decompile it. And for simple programs like this, it'll work. We have an application called IDA. Oh my God, come on. Okay. So we have a application called IDA that you can run on this kitten binary. Actually, there are several different programs like this, these reverse engineering tools that are installed here. And if this loads up, what it will try to do is analyze this binary and recover some semblance of the original C code, even without the C code. But it's a very imperfect process. And oftentimes, the process breaks down altogether, and you can't actually get back to the C code. In which case, if you're reverse engineering to find bugs in compiled software, then you have to look at assembly. The same way, if you are writing exploits or trying to understand the impact of vulnerabilities that you find in compiled software and binary software, the assembly is a critical part of that. So here we are writing assembly. Writing assembly, I mean, you will write assembly in the course of writing exploits. Outside of writing exploits, you won't be doing an enormous amount of assembly writing in your day-to-day lives. But in cybersecurity, you might be doing a good amount of assembly reading. And the goal of this module is to make you understand assembly basically as fast as possible. I think we might be at a performance level that makes opening this file impossible. That's unfortunate. Did that answer your question? Ah, okay, here we go. Loading.
Is this working out the home directory for all these IDA operations?
Yeah, it is. Should have thought that through better. Cool. Other questions while this loads? See on Twitch. Up. Yeah, Twitch had a mini discussion about this decompilation topic. I don't think this will finish. Okay, so we'll push probably over the next couple of days some more, oh, here we go. Hold on. Okay, here's the assembly in our IDA reverse engineering tool. If I hit tab here, it is going to do its best to convert this into C code. And it'll do a pretty good job for this small thing, right? It gets it pretty good. This is incorrect. We didn't pass into the open call an NFP variable, but it gets it pretty close. Sometimes, as you can see, even on this small things, it messes up. And there are reasons behind why this it messed up in this way, but it does. But sometimes it messes up real bad. Sometimes it and then even when it is correct, and you can use this to spot vulnerabilities to actually understand exactly how they work, you need to go to the assembly. Yes. It's tricky. The question was, is there something that we can look to see if the conversion from C to assembly was, or from assembly to C was correct? You can trust that your conversion from C to assembly as you're compiling. You can basically trust your compiler. I found in all of my times of saying the compiler messed up here and that's why my code is crashing, that has been true once in my entire life. But the decompiler is a different matter. You can assume that any decompilation that you look at doesn't match the original code. For even this 4 lines of C doesn't match the original code, right? So now, how to know in what ways it doesn't match the original code? In the next module, we'll look into this, and it's oftentimes basically if you see code structures that just no one will make, like tons of nested while loops with breaks all the way out, that's likely a incorrect recovery of some code structure.
I think part of the issue is, as we'll learn in the reverse engineering module, is that this decompilation is technically not incorrect. It's technically, as you'll see in the reverse engineering module, technically passing in B, it's ambiguous if that's happening right now. But that'll be next module.
Yeah. Cool. Okay. This module, we'll learn assembly. Next module, we reverse engineer some incredible stuff. All right. Let's do it. All right. Catching up on final. Did the editor? Yeah. So someone on Twitch asked me if I received an EtherCap mug, and I did. Thank you very much. So I'll bring my EtherCap mug to. Did I post that on Discord? I didn't. I'll post my new EtherCap mug on the Discord now that I'm an EtherCap pro. All right. Goodbye, hackers.